So we're looking for N. So if you remember from the formula for the confidence interval, we use this as M. And we can find a new formula called the sample size, right? And it's Z star sigma over N squared. No, sorry, M squared. That's how we're going to find the N. So it's this formula here. And you have 1.96, you have 0.25, and you have 0.02. And it should work. Try that.
Got it. Perfect.
Right?
Okay.
So which part confused you?
The first one, I use another formula, so
Which one did you use?
the other one, let me check.
Tatiana, you asked me to fix the connect exercises and I never fixed it, did I? You
No,
asked me.
I'm trying the number
Tatiana?
I didn't try them. I'm going to do them today.
Oh, okay,
So-
good. So I will adjust that and I'll send a notice about my, if people want to try them again. Because I didn't have a chance. I actually forgot, but I didn't have a chance. That's why it was easy to forget. All right. So I'll look at that today after class. So for this problem, this is 1.96, this is 0.25, and then this is 0.02, and it should work. Okay, so those are the options. Don't forget to square.
got it. Yeah. Thank you.
Good, good. Any other questions like from the, but that's from the Connect, so I just gave you the answer, but it's okay. Give away some of them.
One bonus point.
It's okay, yeah. Carolina from the mock exam.
Yeah, good morning. I had two questions. The first in section B, question one of the mock exam. Um, we have the residual formula and I used like, bueno, lo voy a decir en español.
Sí.
Tenemos la Y de las observaciones menos la Y de la predicción.
Ajá.
Pero in the answers, it appeared like
Okay,
Y
let me look.
de la predicción es menos Y de observación, como al revés.
Okay, let me see what happened. So I'll look at the clouding.
Ujú.
Hmm. Hmm. So you said part B, question, this one here, right?
Sí, la segunda parte. No sé porque es Y menos Y.
The formula
Eh,
here,
Yeah.
we always subtract observe minus predicted. So this I actually, since I was young, and learned it, I have like a way to remember the subtraction, because if you subtract them the other way, you get obviously different results, right? So yeah, it's always the observed value. So this is the observed value. Calculate the residual corresponding to fish fillet. So you go to fish fillet, and protein is okay, let's read this thing. Give the amount of protein grams on the amount of a number of data coefficient. Find the least squared of fat versus protein. So when I write it like this is Y versus X. So protein is X and fat is Y. Any questions about that? So the first one that I say is always the Y or J. How you guys say it, J. So this is X. So if for fish fillet, it's here, right? So this is the Y for fish fillet. That is observed. So it should be observed minus predicted. Now, the way you remember it's observed minus predicted is you use the alphabet. In statistics, they use the alphabet a lot for putting things in order. So LMNOP, observed comes first and predicted comes second. That's the way I remember. So, because that will force that, the reason they do that actually is because they want the residuals above the line to be positive, and this will force the residuals above the line to be positive, and yeah, ones below will be negative. So that's why I get a negative here. Is that clear?
Sí.
Okay. You did the reverse, right? So maybe you saw somewhere it was the reverse.
Yeah.
Yeah. So just yeah, put that somewhere on your formulas or somewhere. Like I told you to use the formula sheet, add this one, just like residual equals observed minus predicted in words, or Y minus Y hat, so you can remember, because that's a very easy thing to get wrong. But that does have a rationale. The rationale is that you want the residuals above the line to be positive, and this will force them to be positive, and the ones below the line to be negative. Very good.
Ok, gracias.
Gracias.
Entonces, la otra pregunta que tenía era en esa misma sección, la pregunta 2. No estoy segura cómo sacaron el 15%.
Oh, okay. Okay, yeah. So whenever I combine two concepts, students get confused, right? So I am combining here what you learned about probabilities with what you learned about binomials. So binomials, we find, where's the 15? It's here, right? No, is this the 15? The
En la
15,
primera parte,
yeah,
ahí en la
the 15.
probabilidad de A o A o B.
Yeah. So to A or B, okay, so probability A or B. I'll tell you what it is. Okay, B. Okay, so B or AB. So this is just a probability theory we learned in in module 7 in el 7. And then you have to go, because they're mutually exclusive, either you can be B or AB. Sumando hacen 15. So I didn't put the step where I add them. Are you seeing the paper right now?
Yeah.
Okay. Does that make sense?
Ok.
So you just
Pusieron,
it's because of the probability formula for mutually exclusive events. Either someone is O, A, B, or AB. But if they are B or AB, you can just sum. Remember back to the rules. We can just sum them. Disjoint events. These are disjoint events.
ok.
Okay, so then so it's confusing because, oh, I don't remember, where did we get that from? We learned it already, and I'm going to use it here in the binomial in module 8 or 9. No, module 8. Say in module 6 and 7, I did probability. In 8, I did binomial. So yeah,
Okay.
that might be confusing, but that's where it comes from. I'm just summing these two because of the rules of probability for disjoint events.
Ahí lo que usted hizo fue 15 entre 5.
Exacto. Exacto. Mhm. Mhm.
Ok. Gracias.
These are actually porcentajes. Son todas porcentajes. So I can just sum them. Okay, good. Not another question. I'm glad you're reading that. Otra preguntas. Okay, so if there's no more questions, I'm going to continue with the last row of the formula sheet, and we will focus on the t distribution today. Okay.
Professor, I have a question in the inference homework. Is the 44?
Oh, inference homework. Okay.
Yes.
Hold on, let me get it. Do I have it here? No, that's not it. Okay, 44.
It's in page 10. Trying it, I have the correct answer, but I was confused because I don't know why didn't use the degrees of freedom on it.
Okay, suppose that the time in minutes taken by a biological cell to divide into 2 cells is a normal distribution. And you don't know mu, but you know this is 3.5. When 16 cells were observed, the mean time taken by them to divide. Okay, so this is a sample. So this is, okay, let me just get that. So this is a sample. Estimate the true mean for a cell division using 98% confidence interval. So you don't know mu, but you have the sigma. So you can use Z star for 98. What is the Z star for 98?
2.326.
And you got this from the T table, right?
Yes.
And then you're going to take, so this is the sample result plus or minus 2.326 times sigma over square root 16. And then just be careful that you do it right. Is this okay?
I think so, but I got confused there because if you knew the sample size, I thought I have to do the degrees of freedom.
Right. You do not, because they give you the standard deviation. So you see,
Okay.
when they say past experience and they do not tell you the sample size, they're telling about sigma. You see, I put the symbol there to help you so that you
Okay.
know this is this. I won't always do it, but I do it a lot just so you get the hang of it. So that needs to be the population one. And if you have the population one, you don't have to use teeth and degrees of freedom.
Okay.
Okay, so that's good that you've got this far in the questions to see. So I trained you to use T through the whole homework, and then I changed my mind. So, to make sure you're paying attention.
That's
All
why
right.
I got confused because in one I have to use the degrees of freedom and then you have the population, but I didn't
Yeah.
know how to
Yeah,
just
if you don't,
identify it.
yes, it's that population.
Okay. Thank you.
Good. So now you can see if you have other ones, it's probably the same problem. Yeah, I'll give you guys a moment to collect your questions. I'm going to get some water. Okay, any more questions?
Yeah, I had on the inference homework,
Mm-hmm.
the exercise 69, I think I used the correct formula, but I'm not sure. Oh, okay, let's go through it.
Okay, Carolina, 69 or 16, you said?
69.
Okay, I see you put it in the chat.
Okay, so I did use like the T formula, so it was like x bar minus mu divided by s divided by square root of n, but I'm not sure. Like I saw the answers and I'm not sure why on the top there's only x bar. I'm not sure if you use x bar minus 0 because you don't have the initial mu.
Right. Okay. Okay. So what you come to here is a matched pairs experiment. This is a matched pairs. You have 4 patients. So this is kind of when we started the course, we talked about matched pairs experiments, and here are the results of one. Okay. So I like this kind of problem because it brings us back to the beginning, and we have learned so much over the semester or trimester. So this is the first patient, and before they had this treatment, they had a blood pressure of 161, and then they had it went down. See, so then they had here 158, it went down, 170 went down, 155 went down. But are these really significant? And the significance is determined by the variation, the natural variation of the numbers, which is captured in the standard deviation. So we need to put these numbers together in a way and analyze if really they this is the difference is so many deviations from the mean, if it's really an outlier result. or otherwise we're going to assume there's no difference, because we're going to assume first there's no difference, and then we're going to test if there is from the evidence. Okay. Because we don't have prior knowledge about differences, so whenever we do experiments, especially, you know, with new treatments, we don't have prior knowledge. So because we don't have prior knowledge, we don't know what the standard deviation of the differences is, like the population data. So this is a very realistic problem. And that's why we teach you T distribution, because that's reality. We end up working with T mostly, unless we have a huge sample, we used T distribution. So, so what do we have here? You're right, something's weird. Like, what am I comparing it to? So let's start the test. This is a hypothesis test or test of significance with the first step before we continue. We're going to start with the hypothesis, and here you're going to see. So what's my hypothesis? Am I working with mu or am I working with P? What am I estimating here?
Mu.
The mean, right? You see it in the words here. The mean blood pressure. So yes, we're estimating mu, and I showed you it's always going to be like this. Now, whatever number I put here, I also, oops. Whatever number I put here, I also have to put here. So what number am I putting here? What am I testing for? Okay, let me take it a step back and let me fix this line.
You're looking for the mu for the before drug.
So exactly. So it's a little bit confusing because I have the before drug, the after drug. What I need to do is I need to convert these into the change. We're going to create a new variable, our new column called the change. So I want to do that. Let me read the question carefully. The visitor interested in blood pressure before and after. The absolute value for the test is testing for the difference in mean blood pressure before and after. So the difference, oops, I'm going to move this away. Oh, there's some update. All right. So we're going to create another column here called A minus B. It's the after minus the before. Okay. So after minus before, what do you get? 140 minus 161 is?
-21.
Okay, keep going. And then here, -10, right?
Yes.
-20.
And -15.
And -15. Okay, so now that we've done that, we forget about those. We just look here. And with this data, this is called the difference data. So we use the difference data, and we find the mean of the differences and the standard deviation. So we find X bar and S of the differences. In the notes, I have like a little D underneath. I'm not going to put it just because I want to make it look as much like what we did before as possible. Once you take the difference, once you subtract them, that's how you should think about them. They're just the difference data. So put them in your calculator. Oh. So you're going to put seconds data, clear, and I put in 21 negative and 10 negative and 20 negative and 15 negative. And I asked for the mean. And the standard deviation. Can you concur my numbers?
Yes.
Yeah.
So I'll just
Yeah.
round them to 2 decimal places. Can you see? Because I think the chat might be covering that. Okay, so let me just go here. Okay, so everyone gets that. So then looking at this, if there was no difference, what number should this be? If there's no difference.
Negative 16.
No. If there's no
Zero.
difference, 0. That's the number. So it's not written anyway. You just have to remember when I look for a change, I'm comparing it to 0. Okay, so when I look for a change or I difference my data or I do match pairs, I check for that it's 0, unless it says that the difference is 10 or the difference is 16. Otherwise, if it doesn't say anything, you got to put a 0 there. So put that somewhere in your notes. And then which sign should I use?
Not equal.
Yeah.
A physician compares a blood pressure before and after treatment with a drug. The blood pressure are as follows. The physician is interested in testing for a difference. Yep, that's it. Just difference. You're right. So that's going to be not equals. Okay, so all we have to find is the test statistic, T. And so, so this would be the hypothesis part. And then I started explaining in the notes that just put the assume and assess together. So you end up with a test statistic equal to your X bar. So your evidence, right? So what's my evidence? My evidence is negative 16.5 minus its mean divided by its standard deviation, which is S over N. So this is S over square root of N is what? So this is the standard error. What's 5 divided by square root of 4? So it's 5 divided by 2.
2.535.
So we'll go 2.54.
2.5.
No, let's do that. Yeah, let's do 2.5 because I have a decimal. So I'll put four decimals. So 2.5.
535.
35.
Yeah.
Oh,
Yes.
okay, you're gonna use 2. Okay, 2 more decimals than we had, so 3. All right, so then that's going to be divided by 2.535. And now what do you get? Looks like
6.51.
yeah. That's the answer. Any questions about it? So that's all we had to do. So I taught you the 5 steps to do a hypothesis test, but in these types of questions, I just asked you to do a few of the steps, not all of them. It's in the long answer part of the test that you will do all 5 steps, but here you just, we just did the first. Okay, so what happened here was that we don't have any population information and we have two data sets that are related. When they're paired, like it's the same patient before and after, this is called paired data, and we take the difference to combine the numbers into one column or one variable of difference data. And then we analyze it as though it's, we want to test if it's just zero. In this case, it's not. So let's go, let me do the review or the introduction of the material. And then we will see, people who didn't get this far. I mean, I hope you got this far and I'm glad you got this far. But let me go through the review. But this is where we're going to end up. So this is a preview of what you can do. Then I also want to look at output, statistical output. Any questions about this? Did you have a question?
Gracias.
Good. Okay, so I think I want to be here. Okay. All right, so we done all of this. And I had you do the homework. So you already know about this row, but I'm going to review, okay? So when we are not given information on the population standard deviation, and this happens when we're conducting experiments on novel therapies or with novel products or services, we don't have prior information. So we're going to rely on the results of a single sample. And remarkably, we can do that, but there's a price to pay. The price to pay is that we moved from the Z distribution, the standard normal, to the T distribution, which is looks very similar. It looks very similar. It's also centered at zero. Actually, let me make it bigger. Looks symmetric, bell-shaped. It's centered at zero, but it's spread out differently depending on the sample size. So it's dependent on the sample size. But it tends to have more outliers. Okay, so the standard normal has 0.3% outliers, remember? Because it's 99.7% within 3 standard deviations. So it has 0.3% outliers in the standard normal. Well, there's more outliers in the T, but as you have a larger sample size, as you have I can't do it on this glass. This actually flattens out. Like you don't see it here so much, but this starts to narrow and then it pinches and removes, outliers from this. So it becomes, T becomes Z, and that property is what we were using until now, or until I do this review, but some of you got ahead, but anyway. So we were using here this row because T with high sample sizes, more than 1,000, pretty much becomes Z. So actually what we have on this table are sorry if I'm making you dizzy. What we have on this table are just 12. And here we have the 12 Z-scores, T-scores. These are just the T-scores inside, and there's only 12, and they're all on the right side because they're all positive. because I positioned it at 0, right? So they're all on the positive side, but because of symmetry, we can determine what's on the left side. We know because of symmetry, if it's a negative on here, then it's the mirror image on the other side. So we work with the degrees of freedom. Degrees of freedom is the sample size -1, but sometimes I'll just say, it matters what the sample size is. And you'll notice what's happening as you're going down. The higher the sample size, what's happening here? Values that were previously over here, they go closer to 0, right? So everything's getting, not dramatically, but slowly, it's getting smaller. So it's narrowing. And so even here, right, we're going from 12.4 to 2.004, 2.042. So it's subtle, but it's shrinking like that, or narrowing. So I have some exercises in the notes just to practice reviewing the T distribution and how you apply it. Let's just do a couple of those, right? How many of you did not get this far? So I know who I'm helping here, or I know how many people I need to help or how slow I have to go. So you all got this far? Do you want me to do this review? I don't have to do this review.
Yeah, I wanted the review.
Okay.
Yes, please.
Okay. So, oops, I'm going too far here. Okay, so can you see the screen? So
Yes.
find
Yes.
the probability. Sometimes I use PR or P. I apologize, but that's, I don't know, I'm inconsistent. But that's the probability that T is greater than or equal to 1.5 for our degrees of freedom 19, because the sample size was 20. So in other words, okay, so we're going to draw a picture to see what we're talking about. Sorry. And I'm going to put T19 here to remind myself I'm working with a T distribution. And then I'm going to mark, remembering zeros in the middle, I'm going to mark 1.5. 1.5 is there, and I want to go greater than or equal. So I want to get this. I want the probability here. Now the table is opposite from the Z table. It gives you the right side. The Z table gives you the left side. Okay, so hopefully that doesn't confuse you, but we're going to use the tail. Sorry. Oh no. They got separated. So we go to the table. We look on the 19th row. And we look for that number, 1.5. Like this is So this is opposite again from the Z table. Rather than being on the margins, the t-scores are inside the table. So we look inside for 1.5 and we don't find it, but we find these other numbers. So let's mark these other numbers. We have 1.328 and 1.729. So where are these on the curve? Get rid of this. So 1.328 will be, say, here. Hold on. And 1.729 will be here. And in between them is the 1.5 that I'm looking for. So let's go back and see 1.328 corresponds to what area to the right, because the table just gives you the area to the right. So I'm going to go with 1.328 corresponds to 10% on the right, and 1.729 corresponds to 5% on the right. So this is 5%, and this is 10%. So the best we can do using just this table is that 1.5 is between 5% and 10%. That's our answer. Now we could also go to Excel and get a better answer. I can show you how to do that. But using this table, which is all I expect you to do on the test, is the answer is between 5 and 10%. Any questions about that?
Yeah, Professor, I had a question why we cannot average those two. I maybe it doesn't make sense, but if I know the explanation, I know I will never do the mistake. That why I ask.
Yeah, so you do not average them because 1.5 is not exactly in the middle. Also because you have a curve here. You can't just divide it by 2. There's more on this side than on this side. So that's why you cannot average. Got it? Okay, so that's why we can go to Excel. So you'll see it's not going to be 7.5. You can't just average these. Let's go see what it is in Excel, and we'll feel more confident that we're doing things right. Hold on, let me get a spreadsheet up. Okay, so I'm going to share Excel. So you see this? Okay, so I press T and I have many options for the T distribution. I want to use the regular T distribution. I can ask for the right tail because that's what I want, right? I want to go on the right side. T dot distribution. Otherwise, it'll go on the left side. So I want the right tail. And then I put X and the degrees of freedom. So 1.5, comma, degrees of freedom 19. So it should be between 1.328 and, sorry, it should be between 5 and 10%. And my argument is it's not going to be 7.5, but let's see. Not 18, 19. Any questions about what I did so far? If I don't put right tail, it'll give me the left side. Oh my gosh, it's 7.5.
Yeah.
So it turns out to be 7.5. Yeah, it's okay. I mean, but in general, that's just a coincidence. It's not going to be exactly. You shouldn't in general.
So you're asking us for the two numbers you were doing before, like between,
Yeah,
eh,
between is fine, but I just wanted to prove that it's not going to be exactly, 7.5 like the average of the two, but it is, and that's just a coincidence. So I'll show the formula for people who want the formula for that.
the thing is, I think Tatiana may have the same reasoning. We are accustomed to having an answer with one number, not like two
Yeah,
numbers.
I know. Well, you can use Excel, just to get your one number and feel better, you can do it. Yeah, I have no problem with that. It's just that in the notes, it's not going to be like that because we didn't use Excel on tests in the past. Other comments here. All right, so let's go back to here. So the answer is
So what we would use like normally would be the Excel.
in real life, you mean?
Yeah,
Yeah, real life, you would use Excel or software.
okay.
Yeah, so here I said the answers are all here. And so again, this is the largest set of note because I have lots of questions and all their answers. So it takes a lot of pages. So so T19 greater than or equal to 1.5 is between 5% and 10%. But when we used Excel, we got 7.502. No, 0.0750. It's 75%, 7.5%. Okay, let's go the other way. So I'll finish writing the answer here. So this is between 5%. I put the smaller one first. And 10%. Now we want to go the other way. So we're going to go with that way. So what's the answer to going that way with the information we already have, with the same degrees of freedom, the same?
We're gonna use the T table. Do we subtract from?
Exactly. Yeah. So we already have the answer going on the right because of symmetry. We just take, or because of density curves and knowing about them, if it's 5 to 10 on that side, then on this side it's 1 minus. So you can do 1 minus 5%. So 100 minus 5 and 100 minus 10 to know it's between 90 and 95%. So I took each of these away from 100. And I always put the smaller one first to avoid confusion, but it's kind of confusing. We can do it on Excel as well. And this time, don't use the right tail, use just the regular distribution. So if I say, I'm just going to copy this. and use no right tail, just distribution. Let me start it over. Oops. I'm missing something here. Okay, so let's do it.
In the notes, we have to add cumulative.
Yeah, yeah, I missed that. So when you go this way, you have to do, oops, 1.5. And then you have to say degrees of freedom. And you have to say you want everything on the left cumulative. So 1. So it's 924. It's weird. Because they should make 100. Okay, yeah, that'll make 100% because that'll be 93 if you round, or 90. Yeah, 90. Okay, anyway, they add to 100. So let me put the formula. So this is the left side, and this is the right side. What's happened?
No, yeah, you're not sum directly to the cell. Yeah.
Okay, so they make 100.
Mhm.
Okay, next one.
So, Professor, I have a question.
Mhm.
In terms of the last test, can we, well, I don't know if, I mean, for this type of exercise, can we just copy and paste a screenshot of this from Excel, or do you want like we're doing manually?
I will let you upload your Excel, but you have to show me your evidence. So you have to show the Excel, you have to upload the Excel file, not a screenshot, not an image, not a picture. I need the
Okay.
formula. So yeah.
So definitely we can use Excel and
Yeah.
then just upload at the end.
Yes, Vanessa. Mhm.
Okay, thank you.
What do you mean upload? Like
You upload the whole document, Excel document, not a
Yeah,
PDF.
I understand. So sorry. Go ahead.
Somebody else was asking, Vanessa, not you.
yeah.
Oh, yeah. No, I'm trying to explain Christina.
Ah.
Christina, do you know? Okay, I will speak Spanish. ¿Sabes cuando en ADME subimos el PowerPoint?
Sí.
Pues vamos a subirlo como un Excel file.
Ah, okay.
Yeah,
Actually.
I can set the import or I can set it to accept Excel or PDF.
Okay. Okay.
Not Word, but Excel or PDF. And but I want, if you're gonna give me the Excel work, you have to give me the Excel work. So I can see that, so I can go and look at the formulas and see what you did.
Right, but anyway, we have to upload a PDF with our formula. I mean,
You
our
should have a PDF. So I guess what Vanessa's saying, if she computed it here and then she can put it on her paper, that's fine. But this would be the evidence of the computation,
Okay.
right? Because I need it in the PDF, like you're writing it all out. Yeah. So
What you wanted to know that we plugged in the correct numbers.
exactly.
Okay.
Yes.
And so in that example, we would have to write A1 plus, I mean, A2 plus A5 gives us, okay.
Yeah, I'll put it here. You don't have to put it. I'm just showing everybody that they add. But
Yeah.
but like you're just saying, yeah, if that was part of your proof. Yeah. Okay. All right, let's do the next one. All right, so now we're gonna go into the negatives. Now the negatives are not there on the chart, but my goodness. So we're gonna draw it first. So negative 1.44. Okay, so we're gonna first of all say T6, right? Because degrees of freedom is one less. And then we're gonna mark negative 1.44. I'll just mark it here. I don't know how exact that is, but I'll mark it. And I want to go this way. And but the table only gives me the other side. So I'm gonna make it like this. Oops. I can play with this. Oh my goodness, no. All right, so let's say I want this one, but the table that I have has everything on the right side. So I'm going to use the right side to help me. So rather than this, I'm going to go over here. Symmetrically to 1.44 on T6. And then the answer that I get over here will be the same size as the answer here. Right? So let's go to the table and go to the 6th row and look for 1.44. So the 6th row, and look at that. I picked one that's very easy. So that's right there. It's exactly, so it's 10%. It's 10% on the right. So it's going to be 10% less than negative of that. So this time it's exact. So remember, there's only 12 here. The chance that you're going to get exactly these 12 is slim. If you remember, the normal distribution had hundreds of scores as z-scores. This only has 12. So this was 10%. So that means this is 10%. So that's your answer. Okay, there's one more of these types. So this is called a type 1 problem. That's how I name them, right? So I'm finding the probability given the number of standard deviations from the center, the mean. So this last one, I want to go greater than negative. Oh, okay, so let's draw that. So I'm here. but I want to go this way. So there's different ways you can do this, but what do you recommend? Oh, and we're using T20. Don't forget to always write that. So on T20, you go to the 20th row and look for that number, 2.086. On the table, though, it's only going to give you the value of 2.086. It's going to give you the upper tail this way.
0.025.
So you found 0.025. So clearly 0.025 is not this, right? This is more than 50%.
Mhm.
So what did you actually find when you looked it up?
Well, do I
You
think
got this side.
subtract it from one and then
Exactly.
this looks like the 68, 95, 97 point.
Yeah, this is just using the same principles. Well, this is just using the complement here. Every T distribution is slightly different than the standard normal, but yeah, it feels the same. But when we did that at the beginning with the rule 68, 95, 99.7, I was doing this kind of flipping around and figuring out what we have from what we're given. And we're very limited with this table, right? So if you want to get the precise value, you can put it in Excel to get the precise value. Just remember, well, we would use the RT formula or the RT, function in Excel. So d.dist.rt, and you could find precisely what number it is.
Do you expect the drawing, because it really helps like to draw it.
Yeah, I want you to draw, always draw. Always draw. A lot of students give up drawing, but then they get confused. They just can't do certain things because you need the drawing. And you'll get stuck or you'll do the wrong thing if you don't have the drawing. If you just don't think and you just draw it, you will avoid a lot of problems. Draw it and then think. Because I drew everything here. I drew the number, I put the arrow, and then I shade, and then I go, okay, what do I have to do here? But without drawing it, what in the world? How would you figure that out? I don't know. I guess you could, but it's easier to make a mistake. So I'm glad you follow that. So basically we found what we got out of the table was just the side over here of 2.086 on T20. And that's how she got 0.025. But because if a symmetry, it's the same over here as it is over here. But we want this way. So you have to do 1 minus. So you can operate over here using this information. Or you can just draw this and remember that this is just symmetrical. So if you change the sign and the direction, you have the same things from the table.
The part about not the sign. I never mind.
Yeah, let me do this to make it look the same. I'll erase this. So if I change the sign and direction, you see, I have the same thing. The direction and the sign, the direction and the sign. It's the same area. Okay, so that's how you use the table to find probabilities. You only have 12 on the table. What if I give you a probability? Can you find the t-score? That's a backward type problem. So I will draw it, but this is actually easier when we use the t-distribution. And this is more of what we're going to be doing with the t distribution. But I took this moment just to give you the mechanics of the t. All right, so I'm going to draw this. Okay, I have to draw it somewhere where to the right is a very small number. So that's got to be, first of all, this is T16. And I got to be here. And what I want to know is what T gives 0.005 on 16. So now you're going to do the backward problem. You're going to work on the top margin and go inside for the t distribution. You're going to go from the top and go down to the 16th row.
Or
16.
is it 4.015?
Yeah, so 16 is here. Oops. 16 is here. And I want to go to 0.005. Wasn't it 0.005?
At
Yeah, it's the 2.92.
2.921.
Yeah, I think you put too many zeros there if you didn't. Okay, so it's this one and 0.005, not 0.0005, just this one.
All right, I got
So
it.
it's 2.921. So it's
Okay.
0.5%. This is 0.5%, and you're at 0.2. So you have you're at about 3 standard deviations away from the mean, 2.921, and that will give 5% above. So you see, on 3 standard deviations away in a standard normal, it's going to be 0.15%, but here we are on 0.5%. So it's a lot more outliers on the t distribution. So what was it, 2.9?
921.
921.
Huh?
Yes.
Yes.
Good. Okay, the other one is easy too. So that's what you can remember. You like the t because it's so easy to get the t score.
Sure, it's gonna get quite complicated now that we did the easy one.
Yeah. Yeah. So this one is going to be, oops. And so you're going to draw this carefully. Now, where do I put my pen so that 0.005% is on the left? The arrow goes left. I have to be over here, right? To correct, to get a small amount on the left. So this is the importance of drawing.
T9.
Say it again. Oh, T9. Yes. On T9. Be careful. Yep. Because if you had T16, then you would have the answer already, but you don't have T16, you have T9.
$3.250, but on the negative.
Exactly. $3.25, right? 3.25, but on the left side, on the negative side. Thank you.
Professor, so in this type of questions, we just need to identify the t value.
Exactly.
Okay.
So remembering what we're trying to do is, yeah, but I could even go further and remember when we did the backward type problems with the z-score, we had to do the unstandardizing, to get
Yes.
back to the variable. And here I'm just interested in the t-score.
Okay.
How many standard deviations are you away? And so this is a negative here. Let me make it clear. This is a negative. That's a very bad way to make it clear. Let me do it again. All right. So you mastered the t distribution. And so you can apply it now. I have a video. I have a video. Sorry, I have a video with the t distribution, but something happened to the video and you can't see the description. So I'm doing this every semester now because I never replace that video, but it's okay. It's important to spend some time on it. All right, so what can we do next? Okay, so it's 1 hour left. All right, let's look at some output. So everything's pretty much the same as before with the testing. I'd like to do this problem, but let's see if we can just look at output together first. Maybe I don't have output with the t. I think most of my output is with the, oh, here. All right. All right, let me get the problem. So I'll just cover it for a second. Okay, so this is the problem here. Have you guys gotten this far?
No.
Okay, a manufacturer of ovens is concerned that the dial indicating the oven temperature for a certain model is overestimating its temperature. 4 ovens of this model are selected at random. The dial on each is set to 300 degrees Fahrenheit. So that's what they're trying to make it, 300. The temperatures are measured after an hour, 305, 310, 300, and 305. Those are the sample results. We want them to be 300. That should be the mean result. We know there's some slight variation, but we want to see on average, is it going to be 300? So our hypothesis test, so everyone has the question, understands the question. I'm going to get rid of this. So what do we have here? This is the output. So what's this?
That's mu.
Okay, let's write the hypothesis test down to be sure. What are we testing, mu or p?
I think it's mu.
Right, mu. Trick question, right? Mu. So we have mu equals.
Is that question number 2 on the 60th page?
This is on question number 2 on the 60 page, yes. That's the solutions. All right, and then what number, what am I hypothesizing from the question? What am I hypothesizing? What should it be? What should the oven temperature be if everything's fine?
300.
Yeah. Okay, so it's supposed to be 300. So whatever number I put there, I have to put here. And then I'm going to test to see if it's what, let's see, what do they say in the problem? Overestimating, you see the word?
Yes.
So we're going to test to see if it's overestimating. So what should the sign be here?
Greater than.
Greater than, yes. All right, so now back to my original question. What is this here?
Mu.
No,
That's your, it's not the alternative mean, but
these are the sample results. All of this is the sample. These are the sample results, the moments sample.
okay.
Okay, so then I'm going to ask you again. What is 305?
That's the population mean?
No,
No.
the
X
sample
bar.
The
results. The sample
temperatures, the
X bar.
Well, sample mean.
Oh, well, yeah, X bar.
Yay!
X
X
bar.
bar. I am glad you're laughing. I don't want to
I'm
cry.
crying in the inside.
It's so many
but
terms. I
now you know, right? Now you know. So there's a number here. The output does everything for you. You just have to interpret. That's why I'm showing you this. Okay, so this is X bar. So that's the sample. So what's this now?
That's S.
Sample deviation.
That's S, right? Sample standard deviation. Great. S. And what's this?
M
Try it again.
M
Confidence level.
N is here. They use the big N in the data, but this is like N sample size.
That's to be S
Uh-huh.
divided by square N.
Yes. So you guys can check. You can verify everything here. That's that.
it's an
Trying to
M.
remember because I saw it in the videos.
Say it
I'm
again.
sorry. It's
I
an
saw it in the videos, but I don't remember everything of it.
It's okay, Maria. Don't worry. You're doing great. You're doing great. Okay. Tatiana.
I'm sorry por interrumpir. Esa fórmula no es M. Standard error mean.
Standard error mean no, it's just the standard error. So remember when I explained that sigma over root n is the standard deviation of X bar. So the sample mean has a distribution with this standard deviation, but we don't have sigma. So instead we have an estimate and we use S instead. So what we call this standard error, we call this standard deviation because we actually have the population value, and this is all the true value, right? We don't have to estimate. This is a parameter. But if we don't have sigma, we have to estimate sigma, and now this becomes an estimate. I can put a hat on it, but we give it a name, so we call it the standard error. It's like it's just a substitute word. When you put an estimate inside of an estimate, it's not a standard deviation anymore. They call it a standard error. So that's why that's there. Okay, so you can confirm all of this. You can go and take the average of the data. There's only 4 values. You can check the S. You can divide it by 2 because this is square root of 4. 4 is 2. Square root of 4 is 2. And you get this. See, this is just double. All right, so what's this? Upper 95.
And
Circle.
That should be the upper limit of the confidence interval.
Right. So these are all the statistics. These are the sample results. These are all statistics here. So let me move this away. But whenever I put a hat or sombrero on things, that means it's an estimate. It's not a population. It's a statistic. Okay. And so the upper limit is X bar plus 95 is 1.96. Uh-oh, it's not 1.96. It's going to be T. So what should it be here? T star 95%. So go find that for me. Times S over N.
1.96.
For T of 3. So N was 4, so degrees of freedom is 3. So you got to go and get
3.8, no, 3.182. I think so.
Let's see. So let's go for the 95. So this is important. So what I want to do, so to be clear, these are the upper tails up here on the top. So if you have a 95% confidence interval, what will be your upper tail? Should be here, right? 2.5. If it's 95% in the middle, then it's 5% outside divided by 2 is 2.5. And then you go down to 3. So yes, 3.182. The other way to confirm that if you're confused is to look here, you see? Go up, from the bottom up, and you see, to remind yourself, you have to have an upper tail of 2.5 to be 95% confident. So the answer is 3.182. So it's not 1.96. No, it's much further away. It's much flatter, right? It's much further away. So 3.182. So that's going to be 3.182. And you can check. You can take X bar. You're going to take 3.182 times this S over N and add it to X bar, and you should get this number. Let me know if you can see the screen. I know I'm fighting with the pantalla showing the classroom.
Professor, then we use here the degrees of freedom because we have S and not sigma, right?
Exactly.
Okay.
Exactly. Exactly. So that's always just going to be the catch. That's going to be the catch. Do I have sigma? If I have sigma, I use it. If you have both, you still use sigma. If you don't have sigma, you use S. S is the second best.
Okay.
So we have, you guys can verify these numbers here in the output. And then we have this. Okay, so what's all this here? What's going on? What would we call this number here?
Null hypothesis.
Yes, so that is mu0. And this is X bar. And this is N minus 1. And this is S. And with all that information, you should be able to calculate the T statistic. P-stat takes the estimate X bar and it subtracts the mean, the hypothesized mean, and divides by S over root N. So it's going to be 305 minus 300 divided by S over root N. We have above 2.0412415. And you should get this number. So verify that, and then we'll talk about the last part, which gives you the result. You get the number?
Yes.
Yes.
Great. Okay, I'll wait a minute more for others. Okay, so everything is there, it's all connected. You don't have to make any calculations. I'm just making them to show you that you can rely on this. You have to know what you have there. I'm just verifying that you know where this numbers come from. And then you have all the probabilities here if you want to do a two-tailed test, a one-tailed test on the right, or a one-tailed test on the left. In our case, we pick, because we want to do this test on the right, we pick the p-value in bold. So they're remembering that the one, so if I, so what did we do in the class was, what we would do with this number is I say, draw this, right? So draw this. And you draw and you put your t-stat on the T3 table, graph or distribution. And we put the t-stat up as 2.4495. Yes, I think there's only 4 decimals. How many are there? 2.495. Anyway, whatever. I'll put it all. 95 or 2.45. So where is 2.45? Is it between two values, or do you find it exactly on the third row? So it's between 2.5% and 5%. Is everybody okay with that? So I say from the small number to the larger, it's between 2.5% and 5%. So this is between and in the output, they actually have, the software is able to estimate it. So it's closer to 5, it's 4.59. Why I can't clean that. Weird. So notice, so then we do the conclusion. The conclusion is what? How do we conclude with all this and the bolded? We compare it to 5%. It's smaller than 5%, so we reject. So in other words, what we found is unusual. I mean, it's very close to 5%, but what we found is unusual. And it means something's wrong. So we believe our sample was correct. So something's wrong with the hypothesis. So we reject the hypothesis that they are well-calibrated ovens. Something is up. They're unusually high. You could have done the two-tailed test. In the two-tailed test, the p-value is 10%. And how do you conclude? You should conclude the same way, right? But you get a different result.
Do we have to provide the 3 results?
No. I'm just showing you which one you pick if you get this data. So all I'm doing here is showing you how to interpret statistical output, because in reality, that's what you're going to be faced with. You're probably not going to make any of these calculations yourself. I teach you that so you know what goes underneath and you can interpret. Now it's very easy to show you what all this is here and the one that you want. But notice that the two-tailed test will have a different conclusion than the one-sided test. So it's important that you know what you're interested in. The two-tailed test will fail to reject. So remember, no matter what test, no matter if it's left or right, no matter if it's one-tailed or two-tailed, its conclusion is always the same. We always use the same concluding statement. Oops. So what's happening is, remember, we're comparing this to 5%. But if we do a two-tailed test, we're comparing our t-statistic to 2.5% on both sides.
So it's more accurate.
So it's going to be, yeah, so this is going to be, it's not going to fall in the rejection. So the two-tailed test, like I said last class, I was saying, if you reject with a two-tailed, you're going to reject with a one-tail because it's going to force you into further and further into the tail, right? You have to actually reject, you're going to have to be far in the tail. But it's not necessarily the case. If you fail to reject on a two-tailed, you could still get rejection on the one-tail. And that's what happened here. So what I'm saying is, if we did the two-tailed test, if we're just interested in the difference to see if it's any difference, so something's wrong, but we don't know if it's over or underestimating. So we just do a two-tailed test.
But the two-tailed test is it's like the one-tailed times 2, or the two-tail divided in 2.
Well, let me show you. So the point is that if I put 2.45 here, and I'm doing the two-tailed test, so in the one-tailed test, I'm comparing this to the p-value, right? So I'm putting the p-value, let me use in black. No. It's just very borderline. It's like, I mean, I basically draw it at the border. What is it to be 5% here? Exactly 5% here. We'll go back to the table and tell me what is 5%.
Two point three.
2.353.
2.353. So it's really right there, right? The black is the cutoff, and we're just under it. So we are in the reject. We basically this is smaller than 5%, and any result that's beyond 2 standard deviations. So when we use the Z table, I taught you 3 standard deviations is an outlier, but then we got more specific and I started talking about the 95% confidence interval and being outside it. This is not going to be related because it's a one-sided test. It's not related to a 95% confidence interval. It's actually related to 5% on each side. It's actually a 90% confidence interval that we're comparing it to, but only on one side. So anyway, the p-value is here, 5%. That's what we're comparing it to. And it falls beyond the rejection region. So this I call the rejection region, and it falls inside the reject region. But if I'm going to have a two-tailed test, I have to split up the 5%, and I put 2.5% on both sides. So that's going to be way over here, right? I'm going to use the same color scheme. So here's my number, 2.45. And this I found out is between 2.5 to 5%. But in a two-tailed test, I have to check on both sides, and checking on both sides is 2.5 here and 2.5 here. So it doesn't fall in the reject region, it's outside. So this would be a fail to reject. So what happens with the conclusion step is still always compared to 5%, because I had to do because I had to do 2 times, I had to go this way and add it to that. It's really high. It's like almost 10%. That's not less than 5. So when we do a 2-sided test, we test on both sides. So I'm trying to say if it's higher or lower. So that's why I get 2 times. And what's the number in the output? 0.09 something.
$17.
17.
Okay, so a couple of things from here is just because you reject in a 1-sided doesn't mean you're going to reject in a 2. And I was trying to get at that last time. But if you reject, so just remember, if you reject on a 2-tailed, you will reject on 1-tail because it's forcing, it's really far in the tail. It's really far away if you reject on a 1-tail. It's going to be outside here. Sorry, on a 2-tailed. If you reject on a 2-tailed, it's far away. It's very different. It's very much an outlier. So you can assume the results for the 1-tail, but it's not the case if the 1-tailed rejects that you're necessarily going to have a 2-tailed rejection. Anyway, I'm not going to test you on that specific understanding. I'm just trying to take away, I'm trying to put it together. You know, if you have information, if you want to find out, you know, if something is strange, and you think it's higher, do a 1-tail test and you will find that there's a problem, right? So we found a problem. But if we did the 2-tail test, we wouldn't have rejected. But we shouldn't do a 2-tail test because we see that it's above. We see the numbers are consistently higher. They're not lower. So we shouldn't do this. It will end up failing to reject and not giving us the right answer, basically, that we have a problem. Okay, so you kind of take a sample, you see that it's greater, and you're already suspecting it's going to be greater, so do the 1-sided test. Anyway, I'll never ask you which test to do. I'm just trying to give you a takeaway about the relationship with these tests. I'm always telling you which way to go. All right, so we want to take a 5-minute break and then we'll do some more problems.
Yes.
Or do you guys want to go? I can stay
No,
with you.
The
No?
break.
Okay, take a break.
break,
Let's take
please.
5 minutes. Yeah, let me just say, you know, I don't want your test entirely in Excel because then everyone can just share their Excel and that's going to be defeating the purpose. I want you to do your work manually, but you can use Excel like you would your calculator, but just submit your results in Excel to me as evidence along with your PDF of your work. Okay, I'm back. All right, so where should we go? So should I just do some, okay, let's talk about, let's go through the formula sheet. Okay, so we've already looked at these exercises, just, it's very similar to what we did before in inference. This is inference on the mean with sigma unknown. So this would be the confidence interval. This is for testing hypothesis, and there's nothing here. Why is there nothing here? Let's try, I know, I'm pretty sure I mentioned this in the videos, but I'll do it here as well. Remember how we did this in the first place? We began with saying call this M, and then I write it out like so, M T star S over N, and try and isolate N. So if you try and isolate N, it would be N equals Z star S over M square. So why isn't that in this column? Why don't I have that here? This is called an analytical solution. I'm able to isolate N on one side and everything else on the other side. But the problem with this is N is not on one side because S includes N. S is, remember, as is this formula, and the N is down here. So this formula here that I made does not isolate N. N is inside of S. So it doesn't make it like impossible. You could, but you couldn't do it like, you can't just find N. You'd have to do something like a iteratively with a computer. You could write a program, or you could use Excel where you're picking values of N and then putting them in here and seeing if you can make the ends on both equal, or anyway, you could do something iteratively to solve this, but you can't just use a formula. It's not going to work. Okay, so basically this is not an analytical solution because N is inside of here. So that's why this is blank. Got it? So basically, this does not isolate N. So it can't be used the way the other ones are. Then you could do it in another way, but we're not going to get into that. It's outside the scope of the class.
Professor, speaking of that, in the video in conference 3, they said to the other class cohort that some pages would not be in the exam. Does that apply to us?
Yeah, because it's on Moodle. I have put all the requirements. If you look, it's called let me get the Moodle page up. You see, it's a distribución aproximada del examen final. It's in there. You see? Omit, omit, omit.
Okay, thank you.
Okay. Okay, tell me where to go next. So just to keep practicing. Do you want me to do different problems? I can get some different problems. Or you want me to work with the ones we have?
Can you do from the homework the inference 73?
Okay. Okay, so some of these are for independent or two populations, and I put it in the notes, but I'm not going to test you on it, just because I feel like I don't have enough time to do a proper presentation of it. So I don't expect you to do that one. So that one is
Okay.
exempt.
Okay.
Like anything that says two sample t-test for independent samples, we're not going to do that. We stop at matched pairs tests.
Okay. Will do.
Yeah, I just feel like it's a little pushing it. What do you think? It's just a lot of material, so I just I leave that out. But you could, I have it in the notes, and you can see how it comes from the other things we've done. It's very similar. But when they start doing this, it just, I think it's over.
It gets a little confusing. That's what.
Yeah, that's why I drop it, because I don't spend time on it, because I think it's going too far. But anyway,
Okay.
you guys could, if you had to do a two. So what the main thing is to know the difference between a paired t-test and a two sample t-test. And for the paired t-test, it's like these are from the same subject, but if they're independent samples, it's from different subjects. And you're trying to see if the populations are the same. So let's say you wanted to study Puerto Ricans in Puerto Rico and Puerto Rico diaspora, people who don't live here but are Puerto Rican. So you wanted to talk about the populations and see, are they the same in terms of certain characteristics? And you can do a test, but they're different groups. They're similar, that you can test, like they're the same, but they could be different.
Okay.
I'm just grabbing that example at the top of my head, but yeah. Or if you were testing, treatment, like usually we like to relay them because, again, this controls for a lot of possible confounding factors if we have the same person, right? It's better. Otherwise, we have to take huge samples. So yeah, so independent samples are different from what we've done here with dependent samples. We call this dependent samples. And there's so much we can do in inference, but I didn't do ANOVA and I didn't do chi-square. I just don't feel like, I'm not going to test you on it, but I put information in the notes if you're interested to read it. But I think after this course, if you really do well, if you get an A, a high B, you should understand enough to do other kinds of statistics. And the main thing is to know what you can and you can't do, or how things are different. So like I said, if you have a dependent sample or an independent sample, so we have to do a different test, and then you can look up and see what kind of test that is. I just have a few of those questions here, not too many. Again, this one just goes back to one sample.
Yeah, I have a few left to do, so I need just to look up for the match pairs and one sample, right?
Yeah, if you have any questions, just email me or text me and I'll tell you it's not included. So like 73 is out.
Okay, will do. Thank you.
Yeah. And then this one, see, this is testing if you know the difference. So the following are the percentage of alcohol found in samples of 2 brands of beer. So these are 2 different brands. So do you think that's paired or not paired?
Not
It's
paired.
not, because
They're different brands. Exactly. So that's kind of, that's kind of like the thing I want you to be able to tell.
Okay.
Uh,
In that case, you asked about the degrees of freedom, so
Mhm.
you should sum them up, because there are 2 brands, right?
yeah,
It's
yeah,
3
it's
for
gonna
each
be,
one.
yeah. The degrees of freedom for this, let me go back to the notes here. I have it in here. I don't want to contradict myself. I did difference of proportions and difference. Degrees of freedom. I think it's just n-1 still with 2 samples. Yeah, you add them up and you take
Okay.
away, I don't know, I don't even have it here. You have to add them up and take away 2, I think. Yeah, here it is. That's why I don't do this, because that's your degrees of freedom,
Okay.
right? That's why I don't get into this, because it takes away from the broader idea of what we're doing, and it makes you have to get very specific.
Okay.
Yeah, you agree?
Yeah.
It's not hard, but it's just like it's taking away from the broader understanding of hypothesis testing and confidence intervals. But usually, if you use output, it will give you these results, and it's important to know what you're getting. So that's the main thing I want to get out of it. And yeah, the degrees of freedom, it's not the same. Similar. And then I talk about the chi-square. I really like the chi-square distribution because it's not parametric. But again, it's a whole thing. I need like another class, and like right now at this point we're reviewing, so I usually let it go. But you can read about it because it's interesting. But you'll see I don't test you on it. I don't have any test questions on it. I just put them there if somebody's keen and they have time to read ahead, because these are also very popular tests. And I don't do anything with analysis, with variance, difference of variances, except for analysis of variance. Oh, and I don't think I put the analysis of variance notes in either, because I don't want to distract you. But the chi-square test is very popular. You can even just read this, and with what you know now, you could even read it and get something out of it. Okay, so we have 10 minutes left. What do you want me to do? Any specific questions? Or you well, we're gonna meet next week. if you want to meet with me, separately, or you have individual questions, you can arrange to meet with me, okay? Just contact me and we can set up a virtual meeting. But otherwise, we'll meet next week before the test, and I'll answer any last questions that you have. I'm going to fix the connect to make sure you have enough tries, and you can see your previous tries. I'm not sure why that got unset, but I'll verify that. Let's see, is there any question?
Professor, at what time are you going to post the test?
It's always at 1 o'clock, 1 o'clock for 3 days.
Okay, thank you. How is the documentary going on? Is it about the statistics and probability that you're doing?
No, no, the documentary is about water sustainability on the island. And I've just been interviewing a lot of, I've been interviewing engineers. I actually interviewed the director of Environmental Protection Agency last week, and he gave me some inside information, but he's retired now, so he actually was able to talk to me off the record about what's going on. But yeah, that there's areas of Puerto Rico that people don't get clean, they don't get, even they're not even connected to aqueductos, and what they do to compensate, and how it's pretty bad. But it's only 3%. I mean, it's 3% of people or households. It's pretty bad, even if it's 3% that anybody's going through that. But in general, the quality of the water is an issue for everybody, the quality of the water and the accessibility to water, and what we're going to do about it. My video is mostly about what people can do about it, and what they should do, and what they can do about it, and what the government can do about it. So that's what it's going to be. I'll invite you guys if you want, if you're interested.
Okay.
Yeah.
Thank
Yeah, it's going to be in I think it's of interest to everyone. I'm working right now just to, right now we're just getting through the whole filming phase, and we're going to work on writing the narration, because we want to make it short and succinct, but that takes a lot more work. So
yeah, it's a big production.
yeah, it's a lot of production. So I'm looking at next August, we're going to premiere. So I'll invite you all. If you don't have if you want, you can send me your personal email in case we lose contact. I mean, you guys are just starting the program. I don't suspect. I suspect I can still use your original UPR email, but if you want, you can send me your personal email. It's a very interesting topic, and a lot of people are interested, and I just have to be politically careful because there are a lot of guilty parties in this problem, but I'm more trying to shift it towards taking personal responsibility to do something about it, because we cannot wait for institutions to when they're broken. We can't expect them to work for us.
Great.
Okay. So you guys, I will definitely invite you to that in August, and I want to do a premiere in the teatro, and then maybe some showings in the general studies building, if you guys know that. If you guys aren't here, I'm sorry, but we're going to put it on YouTube eventually, so you'll get to see it. But we want to use it to get support and get interest and build some sort of network of people working on this problem all across the island. It looks like different pockets of people are working on it, and it's not enough. Okay, Giovanni, I'll take your email. Thank you. All right, so let's keep in touch. If you want to meet with me personally or in little groups, we can do that this week. And otherwise, have a good week, good studying, and just follow the approximate exam distribution. It tells you where to stop. I think, Christina, you asked, where do we stop with the notes? Just look here, it tells you. So you stop at 62. Unless the page numbers got messed up. But I think it's still, you're omitting 63 to 67.
Got it.
Let me verify what the notes I have here, that it's the same as I'm thinking it is. So I say up to 62. Yeah, see, all this stuff that I was just talking about is extra. Yeah, just to here, see? And then when I start talking about two proportions, then that's not included, but you can read about it. Okay, so have a great weekend.
Thank you.
Thank you.
Okay, talk to you
you.
next week.
Bye-bye.
Keep
Thank you,
track of your
Professor.
questions
Bye-bye.
for next class. Bye.
Okay.
Bye.
Bye.